This video is going to focus on how to write equilibrium expressions and how to calculate concentrations at equilibrium. Now, if you've been keeping up with the videos, you might notice these are the same learning targets as your last video. In your last video, we dealt with chemical equation equilibrium, so chemical reactions that are at equilibrium, KEQ. This time we're going to deal with equilibrium for soluble products, so basically for dissolving, and we'll do the equilibrium expressions and the concentration for those. Just to kind of get you grounded in all of this equilibrium constant idea, there's actually lots of different equilibrium constants. Okay? Depending on what you're measuring, there's probably an equilibrium constant for it. So KEQ is the most general equilibrium expression that you can have, but then there's more specific ones. KC is specifically equilibrium based on concentration. KP is equilibrium based on gas pressure. KSP, which is what we're going to be working with right now, is based on equilibrium for soluble ionic crystals. Ka is based on acids in solution. Kb is based on bases in solution. And Kw is actually based on water able to ionize itself. So there's lots of different equilibrium constants depending on what type of equilibrium you're working with. For this unit, we're going to deal with KEQ, which is equilibrium expression for general chemical equations, and KSP, which is the equilibrium constant for ionic crystals in solution, basically dissolving. So just a refresher, we just did solutions, but just a reminder, when you have something dissolving, what's happening? You put a crystal into solvent, it's going to dissociate, right? The ions will come off and be hydrated by the water. As you continue to put more crystals in, what's going to happen is you're going to start to find some of the ions are going to knock into each other and potentially are going to start precipitating out. So we have the dissociation of the solid into ions in solution and then precipitation of ions out as a solid. Eventually, you're going to reach your saturation point as you continue to put more ionic crystal into solution. And your saturation point is the point at which dissociation and precipitation rates are equal. Okay? That's your equilibrium. Same as for chemical reactions, your equilibrium were reactant rate versus product rate. So our equilibrium for ionic crystals dissolving in solution are the equilibrium between dissociation and precipitation. Here's another picture of the same thing, just emphasizing that your solubility equilibrium is dissociation versus precipitation. The amount of solid that's becoming ions and the amount of ions that are becoming solid is equal at equilibrium for making solutions. So the trick to being able to do KSP is to actually be able to write equations for the dissociation of ions and then write equilibrium expressions based on that. This is something you should have a general idea on based on the solutions unit we've already done. An ionic crystal dissociates in water. It dissociates into its ions. So for example, for the compound on the screen here, the silver sulfate, it's going to dissociate into the silver ion and the sulfate ion. Silver is +1, sulfate's -2. So when it dissociates, you include the charge. And then the other thing is, you'll generate coefficients based on how many you have in the chemical formula. So in this chemical formula, you have 2 silvers, so a coefficient of 2 is written in front of the silver. For that first one then, what you have is a dissociation equation, an equation that applies to the dissociation of a silver sulfate compound. Now from an equation, you can always write an equilibrium expression. An equilibrium expression equals the concentration of your products raised to a power of their coefficients divided by the concentration of reactant. So it's silver squared times sulfate. And now you notice I don't divide it by silver sulfate concentration. And that's because, right, why does that happen? It's because you don't ever include solids in your equilibrium expression. So in the end, you're just multiplying the concentration of your 2 ions together, which is why this is usually called a solubility product constant. Okay, it's the product of your soluble ions. I'm going to run through these 3 examples and practice them with you. Okay? The main task is being able to write a balanced soluble equation in terms of how the ions separate. And I know how the ions separate continues to be a challenge for some people. So I'm going to run through how to write the equation for each of these and then also the equilibrium expression that's produced. For our first one, iron hydroxide, this is going to dissociate, and it's an equilibrium, so it's a double-headed arrow. It'll dissociate into iron and hydroxide. These are the ions, so you want the charges. Hydroxide has a -1 charge. Iron, you can infer, has a +3 charge because this ionic crystal is developed based on neutralizing charge. And then the last thing is to add coefficients based on how many. So since you have 3 hydroxides here, we need a 3 there. So that's my dissociation equation for iron hydroxide. If I'm going to write an equilibrium expression for that, it's the concentration of the product divided by the concentration of reactant. So it's the concentration of the iron ion times the concentration of the hydroxide ion raised to a power of 3, because you always take the coefficient and raise the power on that. You don't divide by the reactant because this is a solid, and you never include a solid in your KSP expression. Next one, the dissociation of nickel sulfide. They're going to dissociate into their 2 ions. Sulfur has an ionic charge of -2, which means nickel's +2 to neutralize this. And there's no subscript, so there's no coefficients. KSP equals the concentration of your product divided by reactant. So here's my concentration of my 2 ions, and I don't include this again because it's a solid. Now, one thing I want you to notice is there are charges written on the identity of these ions because they are ions. This is your solubility product of ions, so make sure you have charges written down. And then your last one, silver chromate, this will dissociate into its 2 ions. So we have a silver ion and we have a chromate ion. Silver's +1 as we've memorized, which means chromate's -2 in order to have this at the ratio that it's presented at. The 2 means I have 2 silvers in terms of my coefficients. The solubility product for this then is the silver concentration squared times the concentration of chromate. We're going to tackle the math for this tomorrow in terms of how we can use this equilibrium expression to do things. But this is probably one of your most challenging math things you're going to get in this unit. And the reason it's challenging is because the information about the concentration of the ions all comes from the information about the concentration of the ionic crystal placed into solution. And here's just a small kind of intro concept for this, so it should help you tomorrow. If you put 1 molecule of this into water, in terms of the amount of soluble ions made, you would have 1 chromate ion, but you'd have 2 silver ions produced. So with 1 molecule, you actually end up feeling like you have more than you started with because this falls apart. If we take that to mole then, if you put 1 mole of this in, you would produce 1 mole of chromate and 2 moles of silver. Again, it seems like you made something from nothing, but since mole is just a counting unit, it's the same as counting 1 molecule, you would end up with 2 moles. So if you knew the concentration of this, which is moles per liter, you could figure out number of moles, but you would have 2 times that number of moles for silver because there's 2 times that number of silvers per total ionic crystal. Okay, kind of digest that. We will work with problems on this tomorrow. Go ahead and do the form and have a nice night.